in the, yeah.
Good. So this is a radical equation, so we have to first, since it has only one radical, we have to separate the radical from the rest. And then we have to square, but remember we have to square as a whole. You cannot square term by term. So when we square the left-hand side, we simply get x minus 3. But when we square the right-hand side, how many terms do we get?
3.
Yes, very good. So this is x squared minus 2 times the first times the second, plus the second term squared. Now I know that this is quadratic and I have to just move everything to one side and set it equal to 0. So this is x squared. I have to subtract x, and I have to add 3. It doesn't matter if you put 0 here or you put it here. So, of course, try to factor. If it takes too long, just use the quadratic formula. So it happens that this is x minus 4 and x minus 7, so we get x equals 4 and x equals 7. But remember, we're using a principle that may create false solutions, or we call them extraneous solutions. I have to go back and check. So when I go back and check back to the original problem, and I check 4, I know it's not going to work, because 4 minus 3 is 1, and 1 plus 5 is not 4. So I know this one is useless. Now I'm checking 7, and that's fine, and because 7 minus 3 is 4, the square root of 4 is 2. 2 plus 5 is 7, and I'll say yes to x equals 7.
Did we work on D, which has the absolute value? It's the absolute value of 2/3 x minus 6, the other side of the absolute value, equals 2.
Good. So if you remember, absolute value equations are not linear equations, so there are actually two options. What are the options? The options are this. This quantity could be 2, because the absolute value of 2 is 2. But also this quantity could be
-2.
Very good, because the absolute value of -2 is 2. That's all I need to do. So 2/3 x minus 6 is 2, and 2/3 x minus 6 is -2. Now these are two linear equations, and I'll try to solve those. Here I will add 6 and then multiply by 3 over 2. So 2/3 x equals 8, and multiply both sides by 3 over 2. 2 over 3 times 3 over 2 is 1. 8 over 1 times 3 over 2. Please simplify first, it's always easier, by 2, and get 12. I will repeat the process for 2/3 x equals 4, because when I add 6 I get 4. And the same thing, I multiply 4 over 1 times 3 over 2. I simplify first and get x equals 6. You can always go back and check. It's not a requirement. You can go back and check, of course, but it's not like here. Here I had no choice. It's part of the problem to go back and check. Very good question.
Another one is the question 2, section D. It's -3 is less than or equal to 2x plus 5 over 3, less than 6.
Good. So obviously we're solving for x. I have to eliminate this first. I have to eliminate this second, and then this one is lost. So in order to eliminate the denominator, I will multiply all three sides by 3. Now I need to eliminate this, subtracting 5 from all three sides. And now I have to eliminate this, dividing all three sides by 2. The solution is right there, exactly what you see. And you see a bracket at -7, comma, a parenthesis at 13/2. I recommend writing x in, but it's not required.
And so that's it presented in interval notation?
That's the interval notation, yeah. The interval notation refers to brackets and parentheses, yeah.
And if anyone else has any questions, I don't want to feel like I'm taking the whole class.
Anyone? Anyone, any questions, anything? Anything that you want to try? Anything you want to go back to? Yes, Ben, go ahead.
I have one, but I don't remember if we covered it already previously. I just don't understand why the answer is what it is. So the problem is from 4.3. It is, whenever you're ready, it is log base 11 to the 11x, and it wants me to, or want us to expand using properties of logarithms.
Right, so this is a product. So then this becomes log 11 of 11 and plus log 11 of x. Is that correct?
Yes.
And this is always 1. 11 raised to which power is 11? So log base a of the base is always 1. A raised to the first power equals a. So therefore the final answer is log 11 of x plus 1, or 1 plus log 11x.
Okay. Yeah. I don't write everything out, so that screws me up.
So here are a few examples. Log 10 is 1 because it's the same with the base. Natural log e is 1 because it's the same with the base. Another example. Log base 1/2 of 1/2 is 1. Another example. Log base 3 of 3 is 1. As long as this number and this number are the same, the answer is always 1. Because I can change it into an exponential equation. 3 raised to the first power equals 3. 1/2 raised to the first power equals 1/2. E raised to the first power is E. 10 to the first power is 10. 11 to the first power is 11.
Okay, thank you.
Thank you. Before I forget and before your next question, I want to thank you for participating in this class. I want to thank you for being such good students, and thank you for putting up with all this. It was very tough on both sides, on the college side, on real life situations. And I never thought I would say this, but we basically saw a real application of chapter 4. It was this: exponential function with a base greater than 1. The number of infected cases follow the fastest possible growth. I never thought we would go through this, but this was a perfect example. This is what we have been through. An exponential function which has the highest growth possible, highest rate of growth possible. One day 10, the next day 1500, the next day 5000. Amazing. Next question.
Would we be able to do a piecewise function?
Of course.
It's f of x equals 4 minus x squared if x is less than 1, and x plus 5 if x is greater than or equal to 1.
Good. So the first thing for piecewise defined functions, I have to find a domain, and I'll change this into negative infinity 1, and I'll change this into bracket 1 to infinity. And now it's clear that the function itself is defined everywhere. So then I start my table from negative infinity to infinity. 1 is a key number, 0 in the middle, and 1 somewhere to the right of 0. I have to copy these symbols. If you're using this method, copy these symbols right under 1, and they're touching. To be on the safe side, I would write on this interval 4 minus x squared, because it's between negative infinity and 1. And on this interval, x plus 5. I know that this is quadratic, and I know that this is linear. I know that from transformations, let's for a moment just discuss 4 minus x squared. I know how I will graph x squared. We've graphed this millions of times. Then I know how we'll graph negative x squared. Again, we graphed it many times. So, sorry, I should have written this x squared. Then I know that this is a reflection as negative x squared. And then when I graph up 4, then it crosses at 2 and negative 2. We know that. So this will be the graph, the entire graph of 4 minus x squared. But who cares? We can only graph this function between negative infinity and 1. So only this piece between negative infinity and 1. I cannot graph this side. So I know what I have to plug in. I will plug in, of course, negative 2, because negative 2 squared is 4. 4 minus 4 is 0, which I knew it was going to cross here. I will have to plug in 0, and of course I get 4. And I have no choice, but I have to plug in 1, and I will get 3. Although I'm not allowed to, but this will be an open point. On the other side, I have 6, and at 2 I have 7. So always analyze what you have. This is not the graph, of course. This was just our analysis of 4 minus x squared. Now I'm ready to graph everything. Negative 2, 0. 0, 4. And 1, 3. With an open point. 1, 6, 4, 5, 6, full point, and 2, 7, full point. So as you see, when we write the range, this is at 4. There is a gap between 4 and 6. So for the range of this function, I will write negative infinity to 4 closed, because that point exists. It's not this point, it's that point. Union 6 to infinity. That will be the range of the function in case we're asked to find it.
Can you slide your paper up?
Yes. Is this clear?
Yes. And why do we put a bracket next to 4 and 6 in the union?
Because this point exists. It's not an open point.
Oh, okay. Oh, yeah,
And this
okay.
one is not an open point. Only this one is an open point. Very good question.
This is a question from the final from topics of test 2, number 9, and it says decompose the following function in an inner function of g of x and an outer function f of x, such that their function composition determines the function. H of x equals 1 over the square root of 2x minus 1.
Good. So there we have several options here. One option for the inner function is the first function I apply, and it could be this. When I'm done and I get a number here, then I apply f of x, which is the outer, to this number, which must be 1 over x. That's one option. There's more than one correct answer here. Second possibility would be for the inner, for g of x, to consider 2x minus 1, for example. And for the outer to be 1 over the square root of x. So in other words, I determine 2x minus 1 first, and when I'm done, I apply the function 1 over the square root of that number. And yet there is a third option, but here there is no need. Again, this concept is really not for students who will not move on from this course. But if you need to take Math 230, then you need to understand this concept of decomposing a function into different pieces.
This is from the final topics of test 3, question 12b. And it says solve the equation, present the solutions clearly. It's 1 over 3 to the power of x minus 2 equals 9 raised to x plus 3.
So remember, this is an exponential equation because the variable is at the exponent, it's not at the base level. So I'm trying to present both, if possible, with the same base. And I can. This is 3 to negative 1. And this is 3 squared. Can I apply log to both sides and get the same answer? Yes. But it will take you longer. So obviously I copy the base and multiply the exponents by the exponential rules. So this is negative x plus 2. And this is 3 to 4x plus 6, because we multiply them. At this point, I have exactly the same situation as before. Two numbers are equal and they have the same base. Well, these have to be the same. There is no other way. Which means negative x plus 4, negative x plus 2 equals 4x plus 6. Move terms around. There are no restrictions. No headache, exponential, not log. So I move this and I move this. When I move this, I get negative 5x. When I move this to the other side, I get 4. So x equals negative 4/5.